and we can start the course of today. Then the last time we finished the part concerning analytic ultrametric and functional analysis. Today we start a new part of our course, which concerns the algebraic aspect of linear differential equation. Then, for this part, we will fix a field. It's important to fix when we are studying differential equations. It's important to fix a field which is of characteristic 0. We cannot work with one with characteristic p. Let be commutative example. Mid unit. And the derivation which means that if I take two elements satisfied the Leibniz rule, by K derivation, just I mean that it's scalar. And in particular, but in the next one, we are talking about derivation. The zero map is a derivation, but we will suppose that this is different from 0. Of course, otherwise the theories cannot be. We say that can be a field, and then we will say that it is a K differential field. A differential module is just 3A module. What I mean by freeze, it's just that there exists a basis. With finite one. With K linear map. For the TF. And as an example, just for example, we start by usual one and start by differential algebra. The usual one is if we take the R algebra of function, smooth function, infinite smooth function, and we consider the usual derivation, then it is a differential algebra. Here, the multiplication is the usual one, and the addition and multiplication is just the addition of two functions and the multiplication of two functions. The other one, if we consider, for example, it can be also the ring of series, but here just to give an example of a differential fields, then we consider the fields of long formal power series and the formal derivative. It's here, small k, just small k, but I fixed in the beginning. It's a k differential algebra. No, just here. Here just here k is equal, k here is equal to r, and here just for any k of characteristic different from p. P set. Then, for example, if we fix a differential ring, then for all f in A, this is a differential module of rank 1. And all differential module of rank 1 has this form. Now, are isomorphic to this one. Now, if, and I will give another example, if we fix a linear map as follows, then it's easy to see that an equipped with nabla is a differential module. Indeed. And if we set y equal to 1 and nabla of y is equal to d f of 1, and here it's easy to see that we can, this is exactly equal to fg, because f is the f multiplied by the identity, then can inverse, and we got such thing. And here it is exactly equal to df plus df f1 plus hence it is exactly equal to df n f plus fn which is exactly df multiplying by y plus f multiplying by nabla y. Then conversely, if we fix a basis, if we consider a differential, any differential module over and by fixing, it's just mean, by fixing a basis, it just mean that I will fix an isomorphism from m to a power n. Indeed, if we have nabla the sum of Fe, i.e., then it's equal to nabla Fe from 1 to n. It is equal then we can start. And here we have A, G, E, I, E. And this is exactly multiplying. Mean that we have this, and here we have where G is exactly the matrix, this matrix, and AGE is exactly, if I fix here E, then what AGE, EG, G, 1, 1. Then we call G the associated matrix and we just call this the basis in the basis. Then how we can recover a differential equation, differential system from a differential module? Just any differential module. Indeed. Then if we consider the kernel of nabla, then this is the differential. This exactly define a differential system. And And the differential module define a category that we will define their morphisms. And we have the, for example, if we can construct the dual of a differential module if we consider the set of linear map between differential module, then we can keep it with a structure of differential module. Then we see all the operation that we can do with operation with the differential module operation. And we consider two differential modules. And a morphism. Mean that. Then we will observe if we fix a basis, how we can express this condition. And if we fix a basis of M, this basis of M, then let P be linear map. Now we just want to check what this condition mean. If we consider this condition mean in terms of matrix, and so save it. In the basis, then and let G Here, just it's not in the same sense. We know that for each a linear map, we can associate a matrix, but for a connection, we will associate a matrix in a different way, in the way that I explained before. Then the condition, this condition is exactly the same as th, derivative of th equal to hg minus if g. We just need to write everything, and we will get. This just means the derivation of each coefficient of h. In the beginning, I forgot to say that in the case of let's see. Here, just if I have and the associated matrix here, G is equal to 0, we say it's just something like we take just the derivative of each coefficient. This means it's equal to say that the G is equal to 0. And we say in that case that trivial is a trivial differential module. This is just a remark that should be in the example before. Now, in particular, then if we consider a morphism between a trivial differential module and this module, then is equivalent to say that dh is equal to 0. This means this is just mean because we have that having such a matrix is just such a matrix should satisfy its the column of this matrix should be an element of the kernel of nabla n. Here the n is exactly equal to the kernel of to the rank of n. saying just M here. Otherwise, it have no sense to say that. And if there exists an isomorphism, it's equivalent to say that the dimension of the kernel of is exactly equal. Then this means that we have linear independent vector in the space of solution, and the kernel will have the same dimension as the rank of my differential module. Hence, if then the dimension of the kernel, I didn't say it before, but the kernel is a k-vector space of finite dimension with the dimension of the kernel is exactly as a k-vector space is always less than the rank of M. And in this particular case, it's exactly equal to the rank of N, which is, in that case, we will say if we have an isomorphism between a differential module and the trivial module, we will say that is a trivial module. And in particular, if my differential module admits the set of the solution is maximal, which means that the dimension is exactly equal to the rank of M, then we will say it is trivial. And it means the same thing. Like it means just that there exists an isomorphism between these two spaces. I will just give a notation, and after I will explain from where this notation comes from. Then, as I said before, then we have some operation on differential modules. Then if we have two differential modules, we can construct a new one by considering the A module then to have a structure of differential module, we just need, and since M is free of finite rank and N is free of finite rank, then it is the same for this one, and it is just it's isomorphic to the set of the A module of matrix with coefficient in A. Then this define a connection on this this A module. We start by defining a structure of differential module in this A module to define it up after in the dual of M as a module. And here, especially if we look at the kernel of this connection, then it is exactly the set of homomorphism of differential module between M and N. It's just that this means that this one is equal to 0. Saying that this one is equal to 0 is the same as to say that it's an element. It's an element of this. Now, for the dual in particular, dual of M as then by just replace each element, and we will set its D minus phi, and there are, if it's like for the dual of, if we have a k-linear map and we consider the dual, then between finite dimensional k vector spaces, it can be associated to this matrix. And if we consider the dual, then the matrix will be the transpose of this matrix, which means that the line will be column and the column will be line. The dual is important because after we will see how we can link between a differential equation in the classical way and a differential module. It's not exactly the same. We need to pass by by the dual of the differential module. And this just means that it is p-eg, and each p-eg is equal. Here is minus, and each is equal to a-g. Great. Chronicle symbol. Which means that it is equal to 1 only, it's equal to 0 if E is different from G, and equal to 1 if E is equal to G. Then it remains another operation, which is the tensor product of two differential modules. We need that one also to explain how we'll do it for differential module, but we will explain how we can extend the function, or the word, how we can extend the scalar of my differential module. However, for example, we can if we have a differential module, then we can if we have the associate matrix to a connection, then we can, if we consider the dual, we can express its matrix. However, for the tensor product, it's not that easy. It's not that easy at all. Even in the simple, we can do it only in very specific cases. Plus. Yeah. Now we will consider, we can say, an extension of ring, of a differential ring, because it's preferable to use this this term for fields, but we can say, just to say, if we have a ring, A algebra, which means a morphism between A and B, and derivation defined on B, extending. Then we can extend. We will see why it's important to extend the scalar to B. For example, we can have solution. We cannot have any solution in A, but if we extend the scalar, and sometimes it will correspond to a finite extension of a field, then we can recover some solution, and we will give an example of that. And for example, in a specific case of ultrametric differential equation, we can classify all the differential equation in that case. But it's not the case if the character, if we are working with p-adic. It's just the case if we are working, for example, in the field of formal Lorentz series. Then and this is defined if we have a differential module over and this defined a functor from this to differential module over BD. Which means if we have a morphism of differential module in this category, then we will have it also in this in the other one. And then now we set the meaning. Well, what we set an omega m b is the set of, we say the set of solution of the differential module in the ring B, and which is just the kernel of this connection. And in the special case, if B is equal to A, then we will just put omega m or omega ma. Space of solution of m nabla in B. Then example, as I told you before. Then we consider AD to be the field of formal powers, the field of formal power series. And we consider the finite extension of fields. Here it's too small key. And this derivative extend this one because it's just a sub fields. And consider the differential module, this one, d minus. It seems that it's easy to solve, but if we look for the solution only in A, then there's no non-zero solution. It's reduced to 0. However, if we consider here, it's generated by, because we have T, m is exactly equal to n over m and T minus 1, which is equal to now we pass to an important point of a differential module. There exists a basis, a specific basis where we can express our matrix in a very nice way. And we can link it with the case of a differential equation in the classical meaning. That cyclic vector if and only if, then the following set is a basis. Is a basis of fun. And we call it a cyclic basis. Then in such basis, how my matrix has it's a very nice how the question if we have any of if for any differential module we can find a cyclic basis, the response is not no. But however, for the special case, if my differential ring is a field, then there exists always a cyclic basis or a cyclic vector. And let say be a differential field. I said before that derivative is different from zero. Otherwise, it will not be the same, because if the derivative is equal to zero, it's just the theory of Kerling linear map. And in such situation, we cannot always find a cyclic vector. It would be different from zero. And let M nabla be a differential module. Then exists a cyclic vector. Then we finished the first part of differential method. We defined it in a linear way. Now we will pass to the case of differential polynomial, and we'll explain why we have used this notation. Differential. What I mean by differential polynomial is just, for example, I consider a polynomial, however, the indeterminate is the derivation, and we fix so we can in the literature, you can find that it is also called the ring of twisted polynomial.
同学您好，请在教学楼入口或进入教室后主动扫纸巾码，全程佩戴口罩。
Then the difference that it's the same definition for the addition. However, for the multiplication, since the derivatives don't commute with the element of A, then what we will get, then the multiplication will not be commutative. It just means that if you multiply two elements of A, then it's the usual multiplication, standard multiplication. A and verifying. We just need to define what is it exactly, D multiplying by an element of A, and after that everything will follow by we can be defined by induction. And here just the image of A by the E. This is just an element of A plus then is a non-commutative. Since the derivative is not equal to 0, then we are sure that this ring is not commutative, because there is at least one element for which dA is different from 0, which means that dA is different from AD. And the unit here is exactly equal to 1. It's the differential polynomial that have only one coefficient not equal to 0 and equal to 1. And we know, for example, if we consider a field and we consider the ring of the usual polynomial or commutative polynomial, then we can define an Euclidean division. And therefore, the ring is principal, and we have too many nice properties about this ring and about all module over this ring. Then the question, what about this ring? Since it's not commutative, can we define an Euclidean division? The question is, the response, the answer is yes, but not in the both sides because it's not commutative. We will define the division, Euclidean division only in one side, and we will got almost all the result of commutative ring of polynomial. We will got it for differential polynomial, but it will, for example, except for example for the functoriality, it will not be unique because it's only from one side. That's why, because we can divide from this side, we got a result, and we'll divide from the other side, we got another result. I will give an example of that. Then, the Euclidean division will be defined by induction, and it is in the same way as in the usual one. Since we will consider later left a module, then the Euclidean division will be in the right side. Then let the and different from 0. SD here we will suppose that M is less or equal to N. If the M divide an N, just mean, doesn't need that to be unique, just to say that there exists an element A such that N is equal. Here is commutative, it doesn't matter. Then and here, just by saying that AN is different from 0, it just means that the degree of P is, we can define also the notion of degree. It is the greatest index for which the coefficient is not equal to 0. Here, the degree is equal to S is equal to M. Then by right division, this just means that SD is in the right side. This one is in the right side. That's why we say that it's right Euclidean division. And why we chose right Euclidean division? Because we need this term to be in the left side. After when we will consider ideal, left ideal, and we will take the quotient of left ideal, we will obtain the left side. Okay. just an example. Simple example. For example, we say AD squared, and we want to divide it, find the Euclidean division by D. There exists an element D such that A is equal to C. And we will do just to then, as I said, then we will obtain this mean CD multiplying by BD. It will not be as in the commutative case. Then it's something like CD multiplying by B plus and here we obtain something of degree 1 plus B D square. Then this means that if I multiply here, then the rest of this division will be C and now we need if C1 is something like equal to DB, then we should have all this this usually just need if B is a invertible element, then it's okay. Here it's better to say it's better to say that BM is invertible. Then the pair will be unique, probably will be unique, and it's such that C multiplying by D is equal to such thing that just we put C1 here. And we will obtain the desired results. Hence, And here it's equal to 0. It's equal to b t c. Since it is, this should be in the left side, and this should be in the right side. We can also make the, we can also define the left Euclidean division, but in that case we will consider right module. But for all our work, we will consider only left. Left. Plus 0. Then we can define the right Euclidean division. Then the point also, be careful when we want to define an Euclidean division, we need to define a map from P D in N, such that and here for this map, the degree is enough for this map, such that for the Euclidean division we should have the P strictly less than G, and for that we have the degree. And division, and each cleft ideal on K D. Then each left ideal E of, what I mean by that is just E subgroup, and for any element in K, any element PD in K D, we have PD is in and any X in I have PD in multiplying by X is still an element. is principal. Then each left ideal, what I mean by left ideal is satisfying this rule, is principal. Which mean, it just means that there exists an element. An element PD such that I is exactly then in other words we can say that is it's not exactly principal, it's just left principal. But we avoid this such a then it's time we can stop here. If you have any questions.